So we're going to be using all our acid and base knowledge or building upon our solution knowledge and applying it to acids and bases for the rest of this chapter. So we've got a lot of lessons on acids and bases. So we're starting with Arrhenius's definition, and then we're going to go into modified Arrhenius a little bit. This will set us up for Chem 30, where we'll do Bronsted-Lowry's definition of acids and bases. So the Arrhenius definition are acids or any species that ionize to form H+ in solutions. We saw that already in that ionization lesson in chapter 5. Generically, all acids that follow this definition are going to follow this generic formula, where HA is meant to represent any acid. Every acid has to have an H in it. That's why we've got an H in the generic formula. And then the A is meant to represent everything else that's left over, which tends to be an anion, hence the use of the A. So when our acid ionizes, we have that, and typically, but not always, a negative piece. So a specific example, if you take hydrogen chloride gas and you bubble it through water, you make a solution out of it, it will ionize in solution. Okay. And you get H+ and chloride. That's kind of a bit of nice ionization recap. Bases, or Arrhenius bases, are those that dissociate to form hydroxide ions in solution. Okay. All Arrhenius bases are going to produce hydroxide. Now, all of our strong bases are going to be a metal plus hydroxide in the ionic compound. So that's why I went MOH is a bit of a generic formula. Okay. We're going to just have a dissociation where the metal is going to be just by itself. I wrote M+, but that M could be 2+ if it was a group 2 metal. It'd be a +1 if it was a group 1 metal. The stoichiometry will change depending on the charge of the metal. So our strong bases from group 1, an example, and the most commonly used base on the planet, sodium hydroxide. You put that in water, and it's going to break up into sodium ions, which does nothing in terms of acid-base chemistry, and hydroxide is why it's an Arrhenius base. And all the basic properties come from the hydroxide. A group 2 metal would be calcium. So you could have calcium hydroxide. You put that in water and it will dissociate. Okay. Now the group 2 metals aren't very soluble, so you can't put very much of them in water. Okay. The group 1 metals and hydroxide are very soluble. You can put a high amount of solute into solution. Okay. So these are two Arrhenius definitions. He didn't realize his definition of an acid, or the way he thought the chemistry occurred, wasn't totally correct. So we're going to go a little bit past his theory or expand it. Okay. That H+ that is produced by all acids doesn't sit in solution by itself. It reacts with the water. So this is often referred to as modified Arrhenius theory. The H+ from the ionization reacts with the water and makes a hydronium ion. Now the structure of water, it's H2O, it's bent, and there are 2 lone pairs. on water. So when an acid ionizes and makes an H+, a positive species, it's going to have a strong attraction for the electrons. And a pair of electrons that's negative will be attracted to that positive, and the two just come together. So that hydrated hydrogen ion is originally a water, but it's picked up a third H and has a lone pair. So that's what we really get. Modified Arrhenius theory is that hydrogen, hydrated hydrogen ion. So a much better way of understanding what happens in solution with acids, not bases, but just acids, is the acid is going to ionize, and then that H is going to get picked up by a water. We get H3O+, and the leftover part of our acid, which I refer to as A-. So I'm going to do both types when hydrogen chloride is put into water. If I just do the Arrhenius equation, that's what we just saw. You just ionize the acid and you get H+. And this is still used today a lot. In Chemistry 30, we do an electrochem unit, and we use the simpler H+ version. We use the Arrhenius theory. But you need to be aware of, that's not really the truth. In the modified, we're going to take the acid and realize that the H+ is transferred to a water. So this H+ ends up with the water. So our water ends up with 3 Hs. Very similar. You can understand acids and bases with either. So what affects blue litmus? It's the H+ in the Arrhenius theory. A better understanding is realizing it's actually the hydronium ion that reacts with blue litmus and turns it red. What's coming. Okay. So you can put an acid in water, you get hydronium. You can put a base in water, a strong base will give you hydroxide. Okay. You can get hydronium or hydroxide just from water. Okay. So we're talking about the auto-ionization of water. So ionization we talked about, a molecule breaking up and creating ions where there was none before. Auto just means it happens spontaneously or automatic. Okay. So water can react with itself, transferring an H from one water to the other. So one of the waters gives an H to the other. So instead of 2 and 2, you end up with a 3 and a 1 count for hydrogen. And this happens in all natural water. You use distilled water in the lab, it's got a little bit of hydronium in it, it's got a little bit of hydroxide. So what is a neutral solution? It's not a solution that has no hydronium and no hydroxide. It's when the concentration of hydronium is equal to the concentration of hydroxide. If we just have the auto-ionization of water, we get the same concentration of both species and would call this solution neutral. And that is a pH of 7 at 25 degrees Celsius. So that leads to what is an acidic solution? It's when it's not balanced. That's when the concentration of hydronium is greater than hydroxide. Okay. There was some chemical that was an acid, and that made some extra hydronium. Okay. There'll still be some hydroxide from this auto-ionization of water. So acidic solutions still have some hydroxide in them, just not very much. Okay. A basic solution, I'm just going to flip the inequality. We're going to have a greater hydroxide concentration. So some base was added to water. We've got more hydroxide, and we've got this tiny amount of hydronium from the auto-ionization of water. So as we talk about the pH scale and pH and pOH, we're always going to have both species in solution, regardless of whether it's acidic or whether it's basic. So the pH scale. So the pH scale is really convenient for us, okay? It lets us show the concentration by only using the exponent part, okay? It makes a nice scale between 0 and 14 typically. As chemists, we're going to use the actual concentration. pH scale, though, is a nice visual aid, and we've got a lot of devices in the lab that measure pH. So we have to be able to do calculations with it. So the actual concentration of hydronium, H3O plus, is 10 to the negative whatever the pH value is. Now that calculation will not have any units, but pHs, when you use this formula, they output a mole per liter concentration. Okay. Even though everything that I typed out in black has no units. Okay. So I underlined in green our formula, which has no units, pH is unitless, we get moles per liter. So hydronium ion concentration, that's 10 to the minus 3 moles per liter. So that's what, 0.001 if I turn that into a decimal. So not very much, way under a mole per liter, way under a tenth, under 100. This would have a pH equal to just the exponent. That's the meaning of where the pH comes from. So 10 to the minus 3, we would express that as a pH of 3. If you had a hydronium ion concentration equal to 10 to the minus 5 moles per liter. So that's much smaller. Decimal 0, 0, 0, 0. 4 zeros after the decimal before you get to a 1. This is a pH equal to 5. Okay. 10 to the minus 3 to 10 to the minus 4 would be 10 times smaller, and then to the minus 5 would be 10 times smaller again. Okay. We're 100 times smaller, but the pH only dropped 2 units. Okay. We're just using that power or exponent. Let's talk about the whole pH scale. I want to talk about pH on the top of my number line and hydronium concentration on the bottom. And I'm not going to write my units in all the time. They're all going to be mole per liter units on the bottom. pH has no unit, so there's nothing to express or convey. And most people are quite familiar that a neutral pH is at 7. If you're less than 7, you're acidic. There's more hydronium. If you're greater than 7, you're basic, or the solution is basic. There's more hydroxide than hydronium. Now, some incorrectly would label 0 as the bottom of the scale. It's not correct. You can go negative. We'll see that mathematically in a second. And for the same logic, 14 is not the top. Typically, you're between 0 and 14, but is by no means a rule. So I have my arrow on the right and the left going off my number line. So what would the hydronium ion concentration be at a pH of 7? The concentration would be 10 to the negative, whatever the pH is, so that would be 10 to the minus 7. So as a decimal, that would have 6 zeros before we get to a 1. So not even 1 in a million. 1 in 10 million is the concentration. If we're at a pH of 4, that's just 10 to the minus 4. If we're at a pH of 1, that's now 10 to the minus 1. That's a tenth. 1 over 10, 0.1. Okay, so the concentration is radically increasing as we get more acidic, which is lower pHs. When you get to 0, we are now 10 to the minus 0. It looks like a dot. I had to write it small, but that's meant to be a minus. And what is 10 to the 0? Hopefully you don't reach for your calculator. Anything to the power of 0 is 1. So a pH of 0 is 1 mole per liter. And you've been in the lab and you've probably seen 1 mole per liter solutions. We tend to use 0.1, which is a pH of 1. Okay? But the strongest we typically make up and use for students is a pH of 0. Okay? But we could go right what would seem to be off the chart, but it's not. Okay? I could go to a pH of minus 1. So what is its concentration? We have to go 10 to the minus, and then we have to go minus 1. Okay. 10 to the minus is the formula, and then the pH is minus 1. Okay. What is 10 to the minus 1? The two negatives just kill each other. So we have 10 to the 1. So that's just 10. So a pH of minus 1 has 10 moles in every liter. Okay? You're at saturation point or close to it for most acids. Okay? It's very rare to have 10 moles in a liter. Okay? Hydrochloric acid, 12 is the max you can get. Nitric is 12. Sulfuric acid, you can actually get 18 moles in a liter. Okay? But getting below minus 2 or getting to minus 2 as a pH is impossible for most acids. So the practical limit is a minus 1 and a bit for the low end of the scale before you just have so many moles in a liter. If you went to the high end, you could have a pH of 16. It's possible. It'd be incredibly basic. You'd have 10 to the minus 16 moles per liter. But again, you've reached the point where it's not even possible to put so much base into a solution that you can get to that high pH. So 0 to 14 is common because the concentrations are sub 1 mole per liter, and that's doable for a lot of chemicals. So I really wanted to connect pHs to hydronium concentrations, and we're just going to end this slide with a little bit of math of using that relationship. Okay. The pH battery acid is 0.55. There's no units to pHs. What is the amount concentration? Okay. We've seen this in the concentration unit. Amount concentration is moles per liter. Okay. Not percent, not moles per mil, moles per liter. So what is the amount concentration of hydronium? Okay. So we're really just pulling down that relationship from above. And we're going to throw it into our calculator and express it as a decimal or scientific notation. So the hydronium ion concentration in moles per liter is 10 to the minus pH. So this is going to be 10 to the minus 0.55, and this will be outputted in moles per liter. Then you need to grab your calculator. We're not going to express it. That's not scientific notation. It's not a proper decimal. We've got to calculate that. So we're going to turn it into a decimal. Now we've done an operation that you're not used to doing. The sig fig rules for multiplication and division is keep the lowest sig figs. Addition and subtraction is track places. Okay? But we're doing a power of operation. So they're different sig fig rules. Okay? So this is a brand new statement, but it's an outcome of Chem 20. The amount of decimals in pH is your sig figs for your concentration. So you only look at the decimal places. So after the decimal, there are two numbers. So I'm going to put two significant figures in my concentration. So 0.28. My two sig figs are my 2 and my 8. Okay. And my concentration is moles per liter. And this is a pretty high amount of acid in solution, or hydronium. So using the formula is not overly complex. You're not going to have much unit conversion to do here. Going the other way, maybe you want to get pH from hydronium. So to determine pH from amount concentration, we're flipping our two variables around. pH is the negative log of hydronium. Okay. And you just have to make sure that you have moles per liter, which you're given most of the time. If you're doing something lab-based, you might have milliliters that you need to convert. Then I'm going to jump right into a question using this formula and apply those sig fig rules that I just mentioned, but in the opposite order. We're going from the concentration to the pH. So solving this, I'm just going to pull down that relationship. The pH, or power of hydronium, that's the P, is negative log of hydronium concentration. If you do have a TI graphing calculator, you cannot hit the subtract button. It will give you an error. Make sure you hit the negative button. So negative log of 0.0035. We have the units we want. We have to input moles per liter. We have it. pH values are unitless. So the units disappear. So the only tricky part, which again is an outcome of regular Chem 20, is that you can do the sig figs. We have two significant figures in our concentration. So when we take the log of it, anytime we express the pH, the sig figs are just the decimal places. So we have 2 sig figs, so we're going to have 2 decimal places in our answer. So the first digit that shows up in my calculator is a 2, but that's not when I'm going to start counting. 2, 4, so that's my first significant digit, and then I have to round the second to a 6. So 2 sig figs, 2 decimals. Light on pH. You need to know, I commonly will ask questions about what's the meaning of different unit changes in the pH scale. I want you to have a good understanding of the pH scale. That's the point of this slide. So we're going to do a little bit of a case study and find the pattern so you never have to do this, that you remember the pattern of what happens when we change by 1 pH unit. Then you can deduce the pattern of 2, 3, 4, 5, whatever you might be asked. So we're going to look at how does pH cause a variation in hydronium, particularly when we change by 1 full unit. So I'm going to start with a pH of 1. So what would the hydronium ion concentration be? I have to go 10 to the minus 1. And now we're trying to develop some patterns. Most of your brains work much better in decimal. So I'm going to write out the decimal version of this. I'm just going to put my units in my heading. I'm not going to write them over and over again. So that would be a tenth. So the hydronium would be a tenth. If I go to a pH of 2, that tells me about the exponent in the concentration. So we're now 10 to the minus 2. And that adds another 0 before we get to the 1, between the decimal and the 1. I'm going to move to a pH of 3. And I'm going to end at 4. And then we're going to look at some patterns. We're going to analyze what our decimals are doing. So pH of 3 is 10 to the minus 3, 0.001. And last, 10 to the minus 4 for a pH of 4, 0.0001. And now the question is, what happens with differing pH units? Okay, we're going to talk about 1 pH unit difference first, then we'll answer the question of 2, and then we'll answer the question of 3. But we're going to look at 1. So this is what I want you to think about. What is the difference there? It's actually the same difference here, and it's the same difference there. It's either a multiply or divide by something is the pattern. So I'm just going to be quiet for a minute. I want to think what is going on in every one of those green arrows. So the answer to all the drops, and even the ones we don't see, 7 to 8 would be the same pattern. This is a divide by 10, a divide by 10, a divide by 10. Every pH unit, the change in 1 pH is a 10 times difference. If you were going up, it'd be a multiply by 10. That's not what I drew. But if you go up, it's a times 10. If you go down, it's a divide by 10. So now we can tackle the question, what is the change? So delta, a triangle in chemistry is used to mean change. What is a change in 2 pH units? So that would be a, let's go down, divide by 10, divide by 10. What's a divide by 10 twice? It's not 20. Yeah, it's a divide by 100. Now, it doesn't matter where I started. I could pick a different 2 pH units. every drop in 2 pH units is a divide by 100. Okay? So it's 100 times difference. It's a divide if you're going to smaller units. It's a multiply if you're going to bigger. So hopefully we maybe see the pattern. I'm not going to write out this one with arrows. I'd clutter my diagram too much. So it's a 10 times for 1 pH. It's 100 times for 2. 3 pH units would be 1,000. Okay. So you could be asked on a test, what's going on in a pH change of 5 to 3 in terms of hydronium? Okay. What is hydronium doing? So your first realization would be 5 to 3 is 2 units. So the hydronium ion concentration, if it's 2 units, is a 10 times 10, 10 times for each. And then you've got to think, is it more or less? Are we getting more acidic or less acidic? So as we go from 3 to 5, 5 to 3, we are getting more acidic. We're going away from neutral. As you drop in pH, you're going from 10 to the minus 5 to 10 to the minus 3. So anytime you drop in pH, it's getting more acidic. So it's 10 times larger because the pH is dropping. 3 to 5, the other way, would be 100 times smaller change. So pOH, power of hydroxide. I jumped right to both relationships because they're identical to the pH relationships, but OH is put in its place. So you could have the pOH, and it predicts the hydroxide concentration. So if the pOH is 4, the hydroxide's 10 to the minus 4. If you know the hydroxide concentration, you're taking the negative log just like you did with the acid, but your brain has to remember, okay, I take the negative log of the base species, I get pOH, not pH. Now the pH scale, it hurts my brain a little bit. I'm wired to think in pH, and most students are wired to think in pH. So I want to contrast the two scales and give you a bit of a suggestion on a test how at least I think of a pOH-based theory question. So I'm going to do power of hydronium on the top, power of hydroxide on the bottom. I'm not going to put all the numbers in, so you don't have to totally break up your number line, but I'll start by labeling 0, 7, and a power of hydronium of 14. Something that most people in society are familiar with, that rough 0 to 14 scale. We have our acidic part, and I'm going to keep the acidic part on the left, even when we go to pOH, and the basic on the right in both scales. And 7 is neutral. I'm not going to bother labeling the neutral point. Now, the two scales work perfectly equal, but opposite to each other. A pH of 7 is neutral. Okay? So that would mean you have a concentration of hydronium equal to 10 to the minus 7. But if it's neutral, that is also your hydroxide concentration. So hydronium and hydroxide are both 10 to the minus 7. I didn't put my units in. So on the pOH scale, you also get 7 as a neutral point. They're both neutral at 7. And this kind of leads to one more equation that really helps us. The two power ofs always sum to 14. So the pH plus the pOH equals 14. Now, I'm not doing sig figs there. It might be 14.00, 14.00, so many depending on the source you're using. So that lets us do more labeling on the bottom. What is the pOH at a pH of 0? 0 and something is 14. That's fairly straightforward math. That's 14. The other side, they have to add to 14, so that's 0. Maybe I have a pH of 5. What is the pOH? 5 and something is 14. That's going to be 9. Okay. If I have a pH of 3, I have a pOH of 11. So let's just look at that pH of 5, and we can use some of our relationships to get our concentrations. At a pH of 5, the hydronium concentration is going to be 10 to the minus 5 moles per liter. Okay. 10 to the minus pH. If I wanted the hydroxide concentration, I'm still going to do 10 to the minus of, but I need the pOH value. 10 to the minus pOH would be 10 to the minus 9 moles per liter. And this is where even in an acidic solution, we have hydronium, we have hydroxide, but 10 to the minus 5 is a way bigger number than 10 to the minus 9. Okay? There's way less zeros. Okay? If that statement confuses you, if I switch it to a decimal, that's the hydronium concentration. The hydroxide, 1, 2, 3, 4, 5, 6, 7, 8 zeros before I get to the 1. The hydronium is much bigger. The 10 to the minus 5 is much more than 1,000 times bigger, 10,000 times bigger. But we always have hydronium, we always have hydroxide, we have both. So we've got a fair number of equations. I just want to summarize them all, and then you need a bit of time to practice these. It's probably worth me throwing in a few basic circumstances, maybe just one. So something basic on the pH scale might be 12, but on the pOH scale, highly basic things are very low. So pOH of 2 corresponds to a pH of 12. So acids have low pHs. So saying acids have low pHs, bases have low pOHs. Opposite. So this does tend to hurt your brain. You have to know what you're doing. For most of you, drawing a little scale like this on your test somewhere and having it in front of you is a really nice visual to keep yourself straight as you're working through acid-base questions. So summarizing everything, so nothing new. We've got pH, we've got pOH, we've got hydronium, and we've got hydroxide. we kind of have these 4 different quantities. Probably the simplest to go back and forth with is the top. Those sum to 14. So pH plus pOH equal 14. Okay. Where we started with were the 2 relationships that let us go from pH to hydronium or vice versa. So pH is negative log of hydronium, and hydronium is 10 to the minus pH. So if I give you a question, hydronium, and what's the pOH, you can't do that in one step. You have to realize you've got to start here, go there, and there. Some of these questions you're going to get are multi-step. I'm going to take that blue arrow out. So I'm not fully done. We've got the other side, which is the mirror, kind of the mirror image, or just the flip might be a better way to explain it. pOH is the negative log of hydroxide. I've been not writing my states in for the sake of space. Or if I want hydroxide, I've got to go 10 to the negative pOH. So that's your relationship. The bottom, I have to leave blank right now. I know the answer. I'll tell you next year when you do Chem 30 equilibrium, we'll fill in that relationship, but we're just not there yet. So as a 20, you can't skirt across the bottom. You'd have to go all the way around the red, the green, and the blue to go from hydronium all the way to hydroxide. Where sadly, you could do it in one step if I was going to tell you how to do it.